Hello everyone, welcome to the measurement and instrumentation video series. In today's video, we are going to discuss about an important topic which is phantom loading. Let us give a design thinking approach to this phantom loading. First of all, why we need a phantom loading? So, in general, we use a large number of watt meters and energy meters. We manufacture large energy meters and watt meters which has current coils and potential coils within it, which is pressure coils within it. But we use lot of test to measure the actual rated voltage of the current pressure coils and the rated currents of the current coils. But to understand the rated voltage and rated current with less power consumption, we need to find an alternative method because we have certain testings so as to measure the capacity of an energy meter as well as watt meters. But those tests consumes more power. So the problem here is that the empathy here is that we need a testing procedure wherein which the power consumed should be less. So to overcome this empathy, here comes the idea of phantom loading. So let's see what is phantom loading. Phantom loading is the phenomena in which the appliances consume electricity even when they turn off. So the disk of the energy meter rotates, which increases the reading of the meter, but the device do not consume power. This type of loading is also known as vampire or virtual loading. So this phantom loading is mainly occurs in electronic appliances. So generally a phantom loading is available in all electronic appliances. So even though the machine is not operating, it consumes some less amount of power, and that is called as phantom loading. So this phantom loading is used to examine the current rating ability of the energy meter. So actually this phantom loading is a indirect method of testing the watt meters and energy meters. So using direct testing method, we will give the current coil and pressure coil with connected to the supply side from the same supply, and hence both will be uh, found operating at its rated voltage and current. But the problem is that there is more lot of power being wasted because this is an actual loading arrangement. So by phantom loading, these energy meters and watt meters will consume less power as compared to the real loading, and because of this reason it is used for testing the meters. So the problem here we have discussed earlier is being overcome by using phantom loading. In phantom loading, the pressure coil and the current coil are separately excited by supply source. The voltage coil is energized from small supply voltage irrespective of its power, and the current coil is energized with a coil is being energized with a separate current source irrespective of its power, and those power values are very negligible. So this is how a phantom loading occurs. Now let's see with an example. Let's take a problem. Consider the DC energy meter having rated voltage of 220 volts and current 9 amperes. The resistance of the pressure coil and the current coil is 4400 ohms and 0.1 ohm respectively. The power consumed by the load by direct and indirect phantom is being explained so as to give a comparison of how the power is being consumed. Is it shows good variations between the direct and indirect loading method. So first let's see the direct method. So the circuit given is the direct loading arrangement. So the supply is 230 volt, 220 volt, and the current coil resistance is 4400 ohms, and the pressure coil resistance is 0.1 ohm. So let's find the pressure coil power consumptions. So we know that power is equal to, since we don't have any ampere readings here, we can take it as V square by R. So here the V square is 220 divided by the pressure coil resistance is 4400, so which is equal to 48400 divided by 4400, which is equal to 11 watts. Now let's find the power consumed in the current circuit, and power is equal to V into I. The voltage is 220 and the current is 9 amps across the current coil circuit, hence the watts is 1980. The total power consumed is obtained by adding the power measured by the current coil and pressure coils, which is 11 volts plus 9980 volts, which is 1991 watts. Now let's check it with the phantom loading arrangement. In phantom loading, the current coil is given a separate supply and the pressure coil is given a separate supply. So the power consumed by the pressure coil is 220 volts divided by 440, which is 4400 ohms, which is 11 watts. The current coil is excited separately by a battery of 9 volts. So it is not 220 volts, it is 9 volts. Hence power is equal to V into I, which is equal to 9 into 9, which is equal to only 81 watts. So the total power consumed is 11 watts plus 81 watts is equal to 92 watts. So now you got a clear idea about what is phantom loading. See, by actual direct loading method, the power is 1991 watts, but actually it is just 92 watts by using a phantom loading method. So the above example shows that in phantom loading, the pressure and the current coil is separately excited. Hence, the power loss is less in phantom loading as compared to the direct loading. I think in this video you have got a clear understanding about the phantom loading with a design thinking approach. So by finding the problem statement and giving a solution to the problem enables us to understand the concepts very clearly. I think that this kind of DT approach has been effectively used in understanding this particular concept, and the example has served the purpose very well. Hope you understand this topic. We'll meet in the next topic in the upcoming video. Thank you.